Hello and welcome to iCANX. I'm Paul Weiss, coming to you from the University of California, Los Angeles, very early in the morning here in California, and welcome to our attendees from around the world. It's our pleasure today to host the fourth round of the ACS Nano Rising Star Lectureship Awards. As you may know, we choose young scientists and engineers from around the world who talk about where their field is going. We also then ask them to write a piece for ACS Nano, and they serve as advisors to us at the journal. I want to start off by thanking Alice Zhang for putting together and hosting this fantastic series. And it's my honor to introduce our speakers today. We have Professors Martin Thuo from Iowa State University, Jun Chen, my colleague here at UCLA, and Marquita Landry from the University of California, Berkeley, a little bit north of here. And let's move on to the next slide. There we go. Yeah. And it's my pleasure first to introduce Martin Thuo, who's an associate professor in materials science and engineering and electrical and computer engineering at Iowa State University. Professor Thuo works at the border of chemistry and materials science, using self-assembly to create, to study and understand hybrid materials and to control their function. I always have a very great pleasure in talking to Martin when we meet around the world. Now let me turn the floor over to Martin. The stage is yours.
Thank you, Paul. My great pleasure, and I want to thank everyone who's organizing this and for the ACS Nano for the recognition. And it's always a pleasure talking to you, Paul, and it's a great honor to be here and talk about this. So today I'm going to be talking to you about functional materials and how we use interfaces. And I want to emphasize the keyword here, nano interface or nanoscale, because sometimes whenever we think about surfaces, we don't give them credit for being really nanomaterials or nano components of materials. My group is soft materials and matter transport. As Paul said, we are in the middle of the country in Iowa. So before I get started, I want to give a conflict of interest. I will be talking about some work that we are commercializing. And so I'm an equity holder at Selfcleaning. So if I get too much excited, ignore the excitement and focus on the science. So what is our problem? We have two key areas that my group tries to look at. One is what I would call new or current problems. And one of these is actually a problem and also an opportunity. As we know, Moore's law has predicted that devices are going to become denser and denser, and they're getting smaller and smaller. But as it gets smaller, we get into this region here where we are now relying on optical and quantum and molecular level devices. And as we get into this level where we're using single molecules as electrical component, the biggest challenge we have is how do we actually build an integrated system out of single molecules? And the benefits of going at the molecule are profound. We cannot even overemphasize why going smaller is good. And as we go there, we are also compounded by the Internet of Things, the need for devices that we can wear. So as we heard last week from the speakers who spoke on Friday, flexible electronics is a reality for us. And as we go into that region, the problem is how do you interface different materials with only in scale at the molecular level, but also in physical property. For example, here is an electrical component built simple molecule components. But the problem is, even if we make this out of single molecule, you have to put metals next to them. But these metallic contacts are tough, they're stronger than the molecule themselves. And also they require to process them at higher temperature, which makes it a big challenge for us to go through here. Getting these new challenges, we have old challenges that we have not addressed yet. One of which is as simple as corrosion. We understand corrosion very well, but we still lose billions and billions of dollars every year due to corrosion. We understand how to engineer the surface of those materials to avoid contact between the here in this case, water that is causing the corrosion of steel.
Hi,
And
Martin.
if you, Yep.
Martin, could you please closer to your microphone? A little bit, noisy. Yeah.
so if you look, is that better?
Better.
Okay.
Much
If
better,
you
thank
look
you.
at if you look at the problem of corrosion, is a contact problem. If you look at the problem of molecular electronics and flexible electronics, is a contact problem, is basically a surface science problem. And so we're interested in this because we believe that if we can master this, the interface between materials, there's a lot of opportunities that we can open for that. Flexible electronics are here with us. And although we are making leaps and bounds in this area from wearable devices to bendable components and even bendable solar cells, the biggest challenge we have right now is to interface these new technologies with the old technologies, the transistor, the semiconductors that we have, introducing metal wires that will allow current to go through all these materials. And at the core of that, this technology, we rely on a very, very old science, and that is soldering. We have to go to solder to join components to these flexible substrates. And this solder has problems that are 5,000 years old. Since the solder was invented in during the Roman reign, we have problems that we have never solved. Some of those problems are structural, like defects. Others are chemistry, where we have interfaces that form intermetallics, mixing of metals, and these intermetallics do grow and can cause problems in whatever we try to join. But above that, when we go to flexible and more smaller devices, we have the problem of heat. And how do we overcome that heat? If you look at the process of soldering, it's nothing more than melting metal and then allowing it to freeze. So if we have a way of having liquid metal, then of course we can eliminate these problems. As we heard last week from the speakers, they gave us a lot of wonderful things about liquid metal. And I believe that if we could be able to get these higher melting point alloys to be liquid, then we can open up flexible electronics and even higher packaging components much, much faster and get more evolved devices. But the bigger picture in metal processing is that it's very energy intensive and wastes a lot of energy. And the thing we have right now is that these kind of devices are not compatible with this.
Hi, Martin. Also noisy. Yeah, I suggest you click out the virtual background. Yeah, you
Okay.
use a video for virtual background. You click out that.
I don't have a video for.
No video. It's your camera. You have choose a virtual background. Zoom.
Yes.
Yeah, you zoom. Yeah. You click that one, the virtual background. Let's see if it can be better.
Oh.
Is that okay?
Choose virtual background. None. Yeah. I just did none.
Yeah. Now can save some, computer energy, I hope.
Okay. So, all right. I hope is that better now?
Yeah, better.
Sounds better. Yeah, it was a little choppy before. Thank you.
All right. So, my apologies for that. So, as I mentioned, the problem we're dealing with was invented 3000 BC, and we have never seen significant advance in soldering until 1994, when we invented lead-free solder. And what I am trying to say here is that we are actually going to, I'm going to be sharing with you some new advances where we are moving this technology. We don't have to wait for another 5,000 years. And our approach is very simple. We rely on looking at material interfaces. And if you think about a material surface, it's basically the boundary between faces. If you take it as nothing more than a surface, then you have a thermodynamic challenge, because you are assuming that at that point in the material, you will have two energy states, which is impossible. So the better way to look at a surface is actually to look at it as a gradient in composition. And we see this manifested in the way we define surface tension. We define surface tension as nothing more than the summation of the interfacial excess and the change in your chemical potential. And here I add dx because there's a dimension associated with that So I argue that surface tension should actually be a multi-dimensional component rather than a scalar component. If you take this approach to looking at surfaces, then how does the surface of a metal look like? We are not the first to look at this. A few groups have looked at the surface oxides of metals. And if you look at a simple metal like detected gallium indium, you find that that oxide ranges from 0.7 nanometer all the way to 3 nanometers. But from this requirement here, that there has to be a distribution, there has to be a distribution to create this interfacial excess. How then can we actually describe this oxide on this simple metal oxide? About 10 years ago, we looked into that problem when I was still with George Whitehead, and we found out that actually, even in a simple binary alloy like this, that oxide is not uniform. It's actually a concentration gradient and is composed of different oxidation states, and the distribution of gallium and indium is almost speciated. You have a lot of gallium at the surface, but as you go to the end of that oxide, you find you have more indium. So these set up a question. Every time as a chemist you see this concentration gradient, you have the question, what is the work that this interface is doing? And can you actually engineer it so that thermodynamically it becomes a very useful part of your material? And so based on this, then we can go back to this definition of surface tension. And if you want to understand the whole oxide layer, we have to think about it as a tensor. There is variation across one direction, across the cross-section, and also around the whole particle. And therefore, we have to do a double integral into whatever definition we had for surface tension. And when you see something like this multidimensional component, it means that thermodynamically, I can engineer this by playing around with the distributional component at the interface to allow me to do something that will affect the bulk of that material. And if I reduce the size enough, I can get to a point where this oxide will actually play a significant role in how the bulk material behaves. So we took that, and I'm going to share with you one main story, and then I'm going to give you two teasers of what we are doing in the lab. And this main story here is going to be about how we make these metal particles and frustrate their solidification so that we can now start building wires and welding components into places that are not compatible with metals and opening new technologies that previously were impossible. So coming back to that idea of frustrating solidification, if you look at the classical nucleation theory, there is a gaping hole in the definition because you don't have any component here that is capturing the role of the interface that I just described. So if we want to understand in totality liquid solid phase transformation, we teach in our classes that once you eliminate heterogeneous nucleation, the only thing you need to worry about is homogeneous nucleation, which will be driven by nucleation and growth. And if I add an extra tension to this, can I have a situation where I inhibit the growth of this seed nucleus by raising the energy barrier significantly, and therefore inhibiting solidification to a significant amount? And our approach, as I mentioned, is to engineer this surface oxide here and make sure that this provides a tensor component, a stress of some sort that will raise the free energy barrier such that these nucleus don't grow and they don't, they require a lot more energy to actually grow to a point where they can cause nucleation. And so the first metal alloy we looked at was bismuth indium tin, a 3-component alloy, and we found that the oxide here, the oxide layer here, even after growing it for weeks, it was about less than 5 nanometer. And since it has 3 components, we asked ourselves, how is the distribution going to look like? And the distribution looks something like this. The most reactive component ends up being all the way on the surface, and we stabilize this using an organic ligand so that the oxide remains very smooth and very polished, so it doesn't have any kinks that will nucleate the material in the core heterogeneously. And then there is a gradient from the most reactive indium to the tin, and then bismuth ends up being at the interface between the metal itself and the oxide shell. And therefore, if this is what is happening, then we have to redefine this, re-express this free energy term for the liquid solid transformation to capture the contribution due to these concentration gradient here and the stress that is generated when this oxide is formed. And if that's the case, therefore, I can have a situation where through entropy composition, I can have the interface dominate whatever is going on in the phase transformation. How do we make those particles? It's very straightforward. As a former mentee of George Whiteside's, you can imagine I'm making things as simple as I can. So here we use a method we call it a slice, and slice is basically shearing liquid into complex particles. And as we shear these particles, we also are doing chemistry on their surface to allow the distribution of those components and the oxide to be very smooth, and also drop them into size that will allow them to significantly undercool. And with this method, we can actually make particles of all sizes, from tens of microns all the way to nanometer scale. And first, we made particles from e-gain, eutectic gallium indium. And as you can see here, these particles are fairly smooth. If you look at the distribution of the component, you see that gallium and indium are distributed evenly. And for fun, when you have very creative students, they do interesting thing with the work. Here, one of my former students assembled the particles and then they mill them. And when they mill them, they coalesce and form this turtle-like structure. Then when we did the same experiment with fused metal, which is now a ternary alloy, we found that we get very smooth particles and the distribution of the components are even, meaning we have a solution in the core. If these had solidified, we would see spin-order decomposition. We would see separation of the different components. And of course, when we take that alloy and we mill it, we get almost a similar structure as we found with its eutectic gallium indium. And as a further proof, we see that, I'm trying to play a video here. Well, it doesn't feel like playing. So this was the video where we mill the particles and you can see them popping and flowing and they coalesce. But also we can confirm by DSC where we see that the metal with a melting point of 62 can be undercooled all the way below minus 40 degrees centigrade. So from 62 all the way to minus 40, and even sometimes you can get to minus 50. It's pretty amazing. And now, since this metal is a low melting alloy and it's a solid at room temperature, what can we do with it? What are the capabilities that we have? The first thing we did was, since this oxide is very thin, we decided to use mechanical force to break it, and we put this and pressed it, and we could make coins and we could make blades. But the challenge with this approach is that, as we know in granular matter, if you apply force, the force tends to be spread to the air walls of the container because it's flowing by point contact. So the densification is not very good at the core, as you can see in this image here. However, if you look at how strain propagates in these kind of materials, you realize that it's very dependent on the Poisson ratio, and so therefore, if you apply shear stress, you're more likely to get more uniform densification. And that's what we find here. We can make really nice films, even very, very thin films out of these particles. Now, if we can mechanically densify and solidify these particles, because once you break the shell, the particles will basically solidify immediately. We can formulate them into inks, which you can draw by hand, or you can use a robotic arm to draw. And here we're just drawing on pieces of paper. And you can see even once you form those lines and you bend it, it's still very conductive. And beyond that, we can actually build more bigger structures like this display system here. We can make touch pads out of this metal. And these are forming very thin metallic films on the surface. But paper is nice and flexible, but we have other more delicate surfaces that we would like to work with. Things like human tissue. How do you actually join those kind of, make these kind of wires on that kind of substrate? Because you cannot apply force everywhere. So we had to devise another way of sintering these particles and forming electrical interconnects. And what we did is we relied on the capillary processing that we are doing on them. When you have a slurry, as you dry it out, you can incorporate a dilute etchant. And as it evaporates and forms these capillary bridges become extremely high concentrated in whatever etchant we have. And it will get to a point where it will locally etch a lot of the material on this oxide until the two particles have to coalesce. And if they do that, they'll form a neck where there is now an interconnect, and that interconnect will go all over the powder and form a well-connected metallic form. And when you do that on a powder bed, this is what you get. You get a thin film of metal that is actually retains its spherical structure, but if you zoom in, you can see the neck connections, and it's very conductive. The resistivity of that material is about 63 microohms, and if we use mechanical force, it's about 58 microohms, and the bulk metal has a resistivity of 52 microohms, and the same thing for thermal conductivity. Now that we can do this without applying any stress, we can actually start now screen printing very fine structures, as I can show you here. This is the screen, and this is what the screen produced on a piece of paper. And you can see the resolution is very decent for this kind of structures. And actually, these are functional electrodes that a local company here was trying to make for some of the materials they were making on a flexible substrate. And then we can take these printed structures and challenge ourselves to go even more delicate structure. Here we start with a simple thing as a leaf. We're in Iowa, we are farming country, so it's important for us to keep our farmers engaged. So we printed on a leaf, we printed on rose flowers, and then also thanks to a very nice reviewer who challenged us to even think of more delicate structures, we printed on a jello. And the way it works on a jello is there's a density difference that allows the particles to settle on top of the jello. And when you apply your etchant, you will actually get to synthetic particles, but you have to use a higher concentration of the etchant here than you use on a rose flower or on a leaf. But the other benefit we have with our method, the slicing method, is that we can tune the polydispersity of the particles. And if we do this, then it allows us now to dictate which proportion of the particles will go where on a textured surface. For example, if I have a very polydispersed sample and I have a very rough surface where I have multi-scale roughness, all the small particles can find their way to the tiniest crevices of the surface, and the largest particles will stay on top. And since we are working with capillary pressure, then we can start tuning the particles we are producing to either a surface like the rose flower so that it packs every crevice on the rose petal, or even a tissue like a brain that is very, very rough and has a very wide range of textures. And the idea behind it, the science behind it, is that if you put a slurry of particles on a textured surface, you will get, through self-filtration, you'll get all the small particles to occupy the deepest crevices, and the big ones will stay on top. But when you sinter these particles, you're going to get a very nice conformal electrodes forming on top of whatever texture you have. And there are statistical tools that allows us to predict very well what kind of distribution we're going to get. And this work just came out of advanced material interfaces. And with this, again, we go back to the rose flower, and we put just a small amount of particles. You can see how they pack on the crevices of those rose flowers. And then when you sinter them, you have a conductive wire inside the rose network. Here, we are forming very thick lines on the brain, but they are conductive, as you can see on the LED that is lighting up. And we can also do it on a very tough tissue like the heart. And here, we are making it on the heart simply because the heart has a very complex surface layer. Although the outer surface is smooth, there is a fluid that is underneath it that may make printing a little bit of a challenge. But since there is a huge density difference, the particles will actually almost like emboss the structure they need based on the difference in density on that surface. But now that we can do that, what else can we do with this? What if we couple the self-filtration and the sintering to make structures that we can lift off? Can we start making mimics of, for example, the rose flower? And if we take a rose flower and put particles and we sinter them, we lift them up. If we start with the opposite, where we take the rose flower but first make an elastomeric mold and then repeat the same process, we will get a replica of the rose. If we use the rose as our template, we get a negative replica of the rose flower. And based on that, we did exactly that, took a rose petal and we filled the particles and filled all the way to the top. And you can see after we solidify this, we can lift them up and get very nice, well-networked structures here. And this work was done by a really, really smart, ambitious student, Julia, from my lab, who had a very short time to finish their thesis, and amazing work she has done. Then if you take the PDMS replica of the rose flower and repeat the same thing, then the structure you end up with is actually very similar to that of the rose flower. Now, what is the sensitivity of this and why would we care about this? One thing that we wanted to challenge ourselves is to see how good we are at replicating the structures we are working with. So we took two cultivars of the same rose flower, a red and a pink rose. If you look at these two SEM images here, they look very similar. You don't see much of a difference until you measure the distance between, or the size of the features, and there's a really, really small feature difference. And we can get the structures replicated, and we measure the average diameter of each of these features, and we see that there's a slight difference between the rose flowers, the A1 and the A2. There's a small difference, and we see the same difference in the structures that we replicate. So we can differentiate between these two flowers based on this metal-based soft lithography. Then, if we're making a rose flower, of course, we have to look for hydrophobicity, because these structures are known to be self-cleaning, but they self-clean in a way that the droplet actually adheres to the surface of the rose. And when we tilted a droplet of water on our surfaces, we see that it doesn't go off. And as is shown in this video here, actually you can flip them upside down and it doesn't fall off, just like in the rose petal. But can we go even further? If we can make a rose petal where we see the addition, can we actually make something analogous to lotus leaf, where there's zero addition, no matter what you try to do? And so here we use some work that we had been developing in the lab to modify the surface of the metal particles that we are using to make the rose flower. And here we're interested in just etching out the oxide and oligomerizing it on the surface to create nucleates and new features on the surface to increase the levels of roughness on the surface of those metallic glosses. And one of the things we used is capillary confinement, because we know that if you have etch component and you have evaporation, and as you form these capillary bridges in tightly packed particles, then you will end up creating a huge concentration of the etched metal ions here, which can polymerize and grow, creating new features on those particles. And when we did that, we can actually create all sorts of features. Here is one of them that is created in the confinement, where the particles are still within the metal mold, within the PDMS mold. And here is another one that after we make a rose flower, we etch it and we grow these hairy kind of structures on top of that. And we can do this whether we have a two-dimensional film or a three-dimensional textured structure of these metal particles. And when we do that, of course we get these very rough, videos are not playing here, but what I was showing here is actually these images in a movie where you put the droplet and it just rolls off. It doesn't stick at all. It just rolling out, and you cannot have the drops stay on the surface of these structures at all, because we have increased levels of roughness and we have more air trapped in there. Now, I want to conclude this section, and I hope that I've shown you that by actually paying attention to the surface of a metal and paying attention to that 4 nanometer component of a 10 micron or 5 micron particle, you can actually engineer the core properties and also the surface properties of that metal particle, allowing you to do things that you could not do before. Right. Now, moving on to the next section, and this work was actually first published in ACS Nano. And it came from our discussion about the distribution of the component of the surface. And we argued that if actually the the components that are distributed on the surface of this gallium indium are actually reaching gallium on the surface, but reaching indium near the metal oxide interface, then we should be able to grow this oxide enough to a point that we accumulate the indium at the interface. And then when the now thickened oxide fractures by thermal stress, it would release very slowly a component that is actually reaching indium. And that would lead to inversion of the composition, where we had gallium at the top and indium at the bottom, but now we would have gallium coming out to the top and indium, indium being on top and gallium being the one that is at the bottom. That's why we call it an inversion. But this will also happen with that adjustment in texture. And we saw in the previous section, texture is a very, very important parameter in understanding how we're going to use the metal. So these hypotheses panned out as we had thought. And we see here, this is an example of a particle of gallium and indium that has been heated up to about 600 degrees centigrade. And you can see now the component that is on top here is very rich in indium. And we confirm the composition of the two tiers of texture by using OJ spectroscopy. And you can see the first layer is very rich in gallium, but the second layer is getting richer and richer in indium as you continue heating this. But then this is a binary alloy. The question is, what would happen when we go even further? And here we took gallium, indium, and tin, gallium. And here, gallium has the lowest E0, so it's going to oxidize very rapidly and dominate the surface. But then indium is likely going to be the second one, and then tin is going to be the last one. And our hypothesis was, can we actually release these in sequence? That we have gallium first, then we get a tier of indium, then we get a tier of tin. And actually, that hypothesis again turned out to be exactly as hypothesized. The only interesting thing that we found is we see a lot of these fractal-like behavior coming, growing on top of the gallium, and they are still rich in gallium. And we are exploring this further to revisit the theory of oxidation of metals, because this is a new interesting story by itself. But for now, we can see that actually we're getting composition inversion. We are releasing all the metals sequentially, and we can confirm that the components that are coming out at each tier are driven by the E0. And this has been observed in nanoparticles where without the presence of oxidation, Dwayne Johnson had actually predicted very well how the inversion happens based on the work that was going on at University of Illinois. But nobody had ever shown this happening with the oxide layers and showing the relation between these and the composition of gradient across the oxide. So we call these chameleon metals because, like chameleons, as you change temperature, they're responding to your temperature change and they're morphing into a different coat. But then based on what we observed with the first layer, we went back and looked at gallium, a unary metal, a binary, and a ternary, and we looked just focusing on that first layer, and we can see that the composition affects the kind of morphology you get on that first layer. And we believe this is due to the fractures that are occurring on the oxide and a composition due to cohesive energy density associated with the miscibility of the components that you have in the alloy. And finally, the last story I wanted to share with you is related to how we can actually now tap into that oxide and ask the question, can we make new materials that actually will perform in a very different way than what we would expect? And here, we decided to exploit the fact that we can etch the oxide, form components on the surface, organometallics, and then assemble them to make high aspect ratio nanomaterials, and then take those materials and make them into oxide-covered, graphene or graphite-covered metal oxides. And the idea here is that if you have a carbon coating on a metal oxide, you change the band structure because there is a huge interfacial dipole that will necessitate creation of new induced gap states. And that changes the band gap of the material, allowing you to do chemistry that you could not do without the presence of that conductor next to it. And so we went back to our understanding of the surface of the liquid, and we know that By definition, a liquid will plastically deform to maintain the interatomic distance. But then that's for a simple liquid. What happens to a liquid like a liquid metal with an oxide sitting on it? You cannot have this kind of reorganization at the oxide shell. So the only place you can have that reorganization is where you have the liquid metal, which means that if I perturb the oxide shell, this metal will compensate and regenerate this equilibrium structure again, as how we have seen with our fused metal and with e-gain. Based on that hypothesis, then we argue that if I start etching the surface of the metal, two things can happen. If I etch faster than the metal can be replenished, then I will get to a point where I start getting mixed metal ions coming to the solution. However, if I etch slow enough that the diffusion and replacement of the material matching from the surface from the bulk, then I will get the same ion throughout, and therefore I can make chelated organometallic adducts of the same metal ion, which then, if I choose my chelates well, I can actually polymerize and self-assemble them to create a material that looks like this. And in this case, the direction 1 will be controlled by the polymerization. Direction D2 and D3 will be controlled by the self-assembly process. So if, for example, if I have a hydrogen bond on this plane and a van der Waals interaction on the other, then of course, the hydrogen bonding components are going to grow faster than the methyl-methyl interaction components that I impose on the other side. And so we went back to e-gain and we said we start with a binary metal because it's simple. And with this, we were able, Boyce Chang, who is now at Berkeley, did a beautiful work here building this story where the balance between the etch rate and the growth was controlled by the thermodynamics of mixing and solubility, delta GM, in the solvent that we chose to use. And we can set up this reaction and wait for months, and this will grow to a point that they're so long you can actually pick one of them and see it by eye. And the metals we chose to target here was gallium, and our bridging ligand was the acetate, and a complementary ligand was a hydroxy. So we were using aqueous solutions where the adducts were not very soluble. And when we did that, this is the structure we ended up with. We had gallium metal center with interloping acetate units and OHs occupying one plane. And the interesting thing with this structure, it had a little twist to it. And that, although it had a little twist, it does not inhibit self-assembly, as you can see in these structures here. And you can even see this is a huge quantity of material that we made. We can also tune the stoichiometry and end up with different kind of structures where we have more water and less acetate to end up with these kind of structures. But those structures end up relaxing back to the acetate with one water or one OH from the water interloping across the metal centers. We can also make these from other metals. Here I'm just showing you from pure gallium or from gallium, we get the same thing. They have gallium beams. We can make it from pure indium or from bismuth tin, and these two also give us indium material. But the more interesting thing about this is after you make this material, since you have organometallics in the system, you can slowly remove them and reduce them to carbon 0 while also sintering the metal center into metal oxide, which will mean that you will end up having carbon 0 sitting on gallium oxide crystallites. And when you do that, then gallium oxide is a high bandgap material. It has a bandgap of 4.6. But when you do something like that, then you anticipate that this bandgap is going to be much smaller, which allows you to start doing things with gallium oxide that you will never do before. And we call this graphitic carbon coated beta gallium oxide. And so when we heated this material, of course, we see the loss of the organic matter and we see a loss of crystallinity. And then we recover our crystallinity at about 800. And this aligns very well with the most stable form of gallium, beta gallium oxide. Well, we did quite a bit of characterization from solid state, gravimetric, XPS, to understand what is going on, and we were interested in both tracking the carbon and the metal content, whether we treated the samples in aerobic or anaerobic conditions. And we see that in all cases, we are retaining some carbon. And one of my colleagues had actually published a paper that says pyrolysis does not remove all the carbon, so we knew we would have some carbon there. And we confirmed that the carbon is graphitic by using solid state NMR. And you see that carbon is only showing up when you burn your sample. It doesn't show up in the pristine sample. So we know that this is from the reduction of the ligands. And also we see it in the color. As you take the pristine sample, is white. And as you start heating it up, you see it turning yellow, turning brown, turning dark brown. And then you heat it in there, it goes all the way back to white. We confirm that this is graphitic carbon, but we have a mixture of graphene and graphene oxide using Raman spectroscopy. And then the final thing that we did, and this was in collaboration with Professor Jinlong Gong from Tianjin, we did a carbon reduction reaction, and we found out that these materials were very selective in the reduction of CO2 to CO, and we never saw any water splitting, or the water splitting was insignificant, which in combination with UVVs, we can confirm that actually the material had changed its band gap, and now it was a mixed band gap material with a band gap as low as 3.2. And with that, I want to come to the conclusion of my talk, and I hope in a very quick way I've convinced you that the surface of a material is actually a very rich environment for us to look for useful things to do with the material. It is autonomous, it puts itself together, but if you design it well, you can do a lot more than I can share in 1 hour. We have a lot of more work that is coming out that is showing actually the potential, the true potential of that thin layer there. We have also been able to create new functional surfaces and coatings that you cannot make so readily with metals. And we can actually now start interfacing metals with systems that are previously have been very difficult to work with. And beyond that, there's a lot more that you can do with the surface of a metal that I cannot be able to share today. Maybe another day, from playing with the thermodynamics and how relaxation happens when the material is in the solid state. What you can do with catalysis, I mentioned that a little bit. We also have a significant amount of work that is going on molecular electronics, and how that very, very small layer there makes a huge difference, not only in the way we form the devices, but also in how you characterize them and the sensitivity you get out of it. And with that, I want to thank the people who have funded the lab. I want to thank all the organizers, all for invitation, and Alice for organizing all this. And most important, the students who do the work. And my many, many collaborators without whom this will not be possible. And some of them are highlighted here. And I know there's many more that I didn't get to talk about the work that we're doing them. And the students who did the work were boys. Jahel helped quite a bit. Joel, who did the inversion, and Andrew and Julia have been leading the work more recently. And with that, I want to say thank you, and I'll be happy to take any questions.
Thank you so much. Let me pull up the slides here. We had quite a few questions as we went, and I think our audience can see what one can do by understanding both materials and chemistry and putting that together. We have a few questions from the audience, and then if there's time, I'll also take the opportunity to ask you something. The first question from the audience is, Professor Thuo, beautiful work. Is the melting point of 62 degrees C mainly determined by the nanoparticle components or by the dimensions?
No, that's the bulk. Very nice question. The melting point is the bulk melting point of the metal. I don't work with the nanoparticles because I don't want to get into size-dependent properties. All our particles are 1 micron and above. So everything we're doing is behaving more like the bulk, not necessarily due to size.
Yeah, very good. Second question. For the pattern printed directly on biological tissues, are there toxicological concerns, or do you see reactions on the tissue or biological materials?
Very good question. So there are different alloys that we have used on that. One of them, the bismuth metal, that one is very benign. Gallium, also very benign. But once you start going into the silver containing, the copper containing, then you start seeing biological effect. In fact, there are some alloys I didn't get to talk about that contain copper that we have seen the adducts that come out of there start repelling bacteria. So they're actually cleaning the space. But I do anticipate that if you have a hypoxia condition, you can etch out the metal ions, and that could have issues with the person or with the performance of the organ. However, if you have a good like you have a good layer of covering on the tissue, then it should be fine. For example, the brain, it has a very thin membrane that covers it. The heart has a very beautiful brain membrane on it. So even if you put the metal particles there, they will not make it to the heart. And then there's a liquid right below it that is flowing through. We've done work also with bones. So with something like the bone, that one we see a lot of integration into the porous part. The trabecular sections of the bone, we see a lot of diffusion and flow of metallic component into the bone. So it's work in progress. I don't have all the answers.
Oh, fantastic. Third, how about the adhesion between printed nanoparticles and different types of surfaces? How did you fabricate 3D features using soft lithography from the nanoparticle templates?
So it's a really beautiful. This is where I encourage students to be creative. That is something my student Andrew pointed to me when he was doing the work on the rose flower. He could see the particles sticking on the rose, and we were like, what is going on? We started thinking about it, and that's when we found out, oh, wait a minute. There's a capillary force that is pushing the particles together. There's densification. Once the particles are very tightly packed, because these are liquid, they are no longer spherical. They become elliptical. When they are deformed, they jump so well. So even before you activate them to solidify them, they're already so tightly packed and they won't even come out very easily. And then when you put in our activator, we have to put something that breaks the oxide so that they become solid. Once they become solid, then that's bulk metal. That's just like any piece of metal you can pick up. When you pull them out, they don't fall apart. They are actually connected. Like I showed where I was showing the necks forming between the particles. We do that with those ones on the rose flower.
Very good. And I think our fourth question is from Alice. Are there new functions after self-assembly?
Functions.
In other words, in the terms of materials function, when you've, I think she's asking, when you put the materials together, have you been able to gain function in some way?
Oh yeah. So the easiest one is to do soldering, right? So I'm trying to make money out of it. So we are talking to the SMTs and OEMs for people who are doing surface mount technology for electronics, and people who are doing electronic manufacturing. There are quite a few of them who are interested in using this. Actually, in fact, Intel has had a big effort of pushing towards low temperature solders. So these particles are actually the first candidate that we went for in terms of functionality, is to make low temperature solders. And because I didn't get to talk about it in the talk, but we can get regular solder balls and bring them to temperatures that are pretty low, way below 100 C. And then those allows you to start using regular solder, the stuff that is in our computers, but with plastics, any plastic you can imagine. So that's where the function is coming.
And
With
and
the
Okay.
stuff on the rose petal, we are actually engineering those to resist wetting. And if you can resist wetting on a metal, then you prevent corrosion. But that's something we are still exploring. Julia is working on that. Hopefully she will deliver soon.
Very good. Well, thank you so much for the beautiful talk and insight, and the your last slide with the what can't we do. I think in terms of your laboratory, you might add the word yet to the end of the title there, because I see you thinking about what it is you'd like to be able to do in materials, and that's part of the reason I always go out of my way to see you and see what you're thinking. And I'm hoping that sometime soon in the new year we're able to do that. And
Yep.
Normally under these circumstances, I'd walk across the stage and bring you a plaque for the ACS Nano Rising Star
Yep.
lectureship. For now, I'm afraid we'll have to settle for this electronic version.
That's
But thank you so much for the talk and for your insight and wisdom. And I know that many in the audience are also looking forward to the career panel we'll have after Professor Chen's talk. So please, stay online for us for that. And thank you once again from all of us.
Thank you. Thank you very much. Appreciate it.
And next, it's my pleasure to introduce our second